Well, today we're going to talk about injection molding. Let me share my screen. Share screen. Share, right? Well, injection molding is one of those important manufacturing processes. If we look around us, there is many parts made by injection molding. For example, if I look at my just desk, the headphone, the Bluetooth headphone that I have, like the enclosure made by injection molding, and any of these headphone also made by injection molding, the part itself and the soft part as well. Another example, like the USB, like this is just the things around me on my desk. The USB converter from A to C or whatever, it's made by injection molding. Again, we have a metal and injection molding over a metal. Sometimes it is called over molding. Or like a USB thumbnail made by injection molding. And the cap of the orange juice, the bottle orange juice that I just drank, made by injection molding. What else I can say? Well, these things, for example, to practice my wrist, it's rubbery things, but made by injection molding, which we'll talk about it later. How can I say it made by injection molding? But one simple thing is we look at these edges or lines. Maybe it's not easy to see from by the video, but shows like the two half of a molds coming together. Or another example, speaking of wrist, I have these gyro things on my desk, which if I rotate these things very fast, then I move my hand, so it helped me overcome these carpal tunnel if I work with a mouse a lot. So it made by injection molding, so like the inner parts, the outer parts, which is like hard materials, and also these rubbery part as well, they made by injection molding. Well, and these small little things like the flosses, like dental flosses, they are also small items made by injection molding. So it is just to give you an idea about like the regular parts that we can see around us. Or for example, I'm just looking at these Terra cane, which I use for sometimes massaging myself, like this. I'm not sure if you guys use. Oh, it feels so good. So it's also made by injection molding. It's very hard and also has some features which show it made by injection molding. And anyway, from small parts to big parts, they're all made by injection molding, and that's one of those versatile manufacturing processes that we can see everywhere. But what made injection molding so attractive? What made it so attractive? Let's take a look at the attributes of injection molding. Well, hopefully you watch the videos and you are now familiar with the concept of injection molding, but simply we inject a molten plastic into a cavity, which we call it a mold, which is in the shape that we want. We let it to solidify and cool down, and we get something, plastic parts that we want. All right. So this is what involves injection molding. So typically, injection molding start with the material, which is in the form of a granule or pellet, like plastic pellet or granule, and we turn it to basically we melt it and we turn it to different shapes that we want. It comes in different colors, and also the price is cheap. I just checked before your class to see if I want to buy 1 kilogram of these, how much it costs. And And on this website, Alibaba, which you can check for yourself. So you can see, for example, like the PP, which is polypropylene, it's about less than $1, less than a US dollar per kilogram. All right, and so you can find like very cheap plastic granule for low price. So then the cost less than $1. All right, and then you make out of 1 kilogram, you can make lots of parts. And if you look at the 4 attributes of this manufacturing, which, if you recall, as we said, for each manufacturing processes, we look at 4 attributes because that's is what we can decide if we want that process or no. So the first one was cost. How much is the cost of 1 unit, excluding the cost of toolings, and how fast we can make 1 part, which we call rate. What is the quality of the part that we can make, and how flexible is the process. By flexibility, if I change the material or if I change the geometry, how easy it is to change it, right, in terms of flexibility. So when it comes to injection molding, the cost is very, very low. So again, keep in mind the initial cost when we buy the tools and the machine is high, but here we talk about an individual parts because usually with injection molding, we produce thousands and thousands of parts. And again, if you recall from the very first session, we talk about a graph, which we said, if let's say y-axis is my cost and x-axis is the number of parts. So at the beginning, if we just produce 1 part, the cost is very, very high because these costs include the cost of tooling, right? And the cost of shop and other things. But as the number increases, the cost becomes smaller. And after many, many parts, let's say 10,000 parts, we just left with the cost of raw materials, labors, and maybe the cost of power that we need, like the electrical power and so on, which we, again, injection molding, this cost is very, very low because we produce lots of parts, like a factory that produce the bottle caps, you can imagine produce millions of parts maybe per day. The rate is super fast. So the rate is very high or very fast. So let me write very fast. So no manufacturing process can beat the rate of injection molding. The quality is acceptable, or let's for now say good. When we talk again about quality, we talk about the surface finish. Usually with plastic, we are happy with injection molding. Another quality is the tolerance or the dimensional accuracy. Again, we can, with some materials, we can maintain a very tight tolerance. For others, maybe we don't care. Like nobody's gonna ask if plastic parts is maybe 0.1 millimeters is smaller or bigger. Again, depends on the application, but the quality is relatively good, but the flexibility is very, very low. That's the negative part of it. And it is clear why, because it involves a mold. And when we change the shape of, like the geometry of the part that we want, we need to change everything. So we need to change the mold. And it's not just the mold. We need to, you will see, we need to recalculate the forces that we need to clamp 2 halves of a mold together. We need to change maybe the pressure that we need to inject the mold into cavity. And it involves a lot of changes. Even we may need to change the machine even for a simple geometry change. even if we change the material, so the geometry the same, the material different, still we need to make some changes. So the flexibility is very low. But still it's one of those attractive manufacturing processes because the cost and rate are very attractive and good. So in this module, we're going to have introduction to the concept of injection molding, or you've already watched some videos, you know what it is. But here we're going to talk about like the properties of two categories of material, thermosets and thermoplastic, which again, in lecture 2 or 3, we talk about it, but I'm just going to do a very quick review here as well. Also, we're going to talk about, which is the main part or the main topics of this module, is we're going to talk about the process parameters, like the viscosity of the plastic. If it changes, what's going to change related to the, for example, the pressure that we need to inject, the force that we need to clamp two half of the molds together, and also how long does it take for a part to solidify. All right, so that's our objective in this module. So let's start with the first part. So if you recall in lecture 3, we talk about polymers, and polymers we said means many units. Let's say if I have a chain of polyethylene, each of these units, which we can call it an ethylene, which is like this portion ethylene, which is carbon and hydrogen. If under heat and pressure, I can combine all of these and make a chain, which is called polyethylene. Similarly, we can have like polypropylene, which is known for PP. In that website, Alibaba, you saw people call it PP, and it's cheap. Or PET, which is again combining of, not combining in terms of mixing, but PET stands for polyethylene, and terephthalate or terephthalane, any of these can be pronounced, which again, you've seen a lot this material. A good example is the beverage, for example, Coca-Cola in these basically bottles. And an important features about them is the pressure that they can stand. Like a regular bottle inside pressure is maybe around 50 psi, but in that video later, if you like to watch, the guy tests how much pressure a bottle can stand, and it goes up to or over 200 psi, which is a very high pressure. Just to give you an idea about this pressure, a regular car tire is going to explode at 230 psi. So what the tire is very thick and it's rubber, right? So if a car tire can withstand, like explode at 230 psi, then I would say 200 psi for a bottle is very impressive. Yeah, later you can watch that video. I put the link in that notes as well. And the reason that we like this material, if you don't want a bottle, if it drops, you don't want it to explode, right? If you drop it, so impact force. It's good for impact force. Otherwise, if it cracks or explodes, it's because the pressure is high, it's going to be very messy, right? So in terms of elasticity and density, where it stands compared with other materials. So on this graph, if you look at the x-axis as the density and y-axis as the module of elasticity. So of course, we know with ceramic and metals, they are at the top right corner. They are heavy, but high module of elasticity. Foams, for example, or wood at the bottom left corner, low density and low, basically, module of elasticity. Polymers stay somewhere in the middle, right? So between metals and wood, we can compare it to some hardwood, for example, maple or oak, but this is where typically they stand. Relatively average density and relatively average module of elasticity. All right.
Question?
Yeah, go ahead, please.
Is there any other material other than polymers that we can injection mold? And there's a question in the chat that how is it to change the color of our pellets or change the size of them, or how flexible is it in that terms?
All right. Two good questions, which you are ahead of me, but a short answer. The injection molding is not just for plastic. Metals also can be injected, can be injected, and with the same process. Sometimes we use the same machine, in fact, to do injection molding for metals, which I'll get to that at the end of this module. In terms of colors, colors is not that difficult if you use the same plastic, because usually the color is in that plastic. They add something to that original plastic. It's not as an additive, or it might be that I'm not aware. However, geometry is a different story, which you will see. I will get to that. Maybe not in this session, next session, I'll talk about it. All right, Ahmad?
Thank you.
All right. So let's look at the stress and strain. So again, with plastic, they have a range from like brittle material, like melamine, which probably, again, you've seen in one of those kitchen dishes, or they can be very flexible and soft, such as the hose that you water your garden, or tough and ductile, such as like ABS, which again, as a kid, most likely you used logo brakes. Somewhere in the middle, like these O-rings, O-rings, without O-rings, you can imagine engines, rockets, and all these cylinders that has like high pressure gas. It would be difficult to seal them. But O-rings, which is a very useful, and they comes in different sizes, from tiny O-rings, like in size of millimeters, to like big O-rings, like 32 inches in diameter O-rings, again, made by plastic. They are flexible and they can withstand like high pressure and high tension. Speaking of O-rings, I remember like before a couple of years ago, I thought that picking and like O-rings for a design is easy. Then later I learned, based on something that I had to design, and I need a ceiling for that. And I need to refer to somebody who was specialized in O-ring design. I didn't know, as a mechanical engineer, one person can spend his entire life designing O-rings. You may think that's boring, but it was really complicated. The size that you need to pick, the pressure it needs to withstand, and the tolerance, how much the shape change under pressure, and so on. Anyway, my point here is plastic can have a range from brittle materials to very soft, to ductile, and very soft and flexible, as you can see in this image. Another thing that we talk about is two main categories of plastic. Of course, we talk about three categories: thermoplastics, thermosets, and elastomers. Elastomers, let's separate it for now, because that's in a range of rubbers and different story. But with focus on injection molding, let's think about two categories: thermoplastics and thermosets. So if you recall, we said thermoplastics, we can remelt them. Like these, for example, recycle bin, if I expose it to fire, it's gonna melt again. So that's thermoplastic. But you don't want your, for example, kitchen spatula or the handle and knob of these kitchen pot to get melted, right, when you are cooking something. So this is where you need another category of plastic, which is thermosets. And the main difference between these two is the cross-link. If you recall, we talked about it, the cross-link between the chain of this plastic that we have, all right? But both of these, we will use them for injection molding. The only difference is the thermoplastic, we can recycle them and we can reuse them. However, with thermoset, that's it. After we made something, we cannot remelt it. So the main things that we need to know is a feature. Again, we talk about it, lecture 2 or 3, is that plastics under heat, their property changes. For example, if I look at the stress and strain again diagram, let's see in this diagram. So let's say this is a stress and epsilon strain. So typically with like a regular plastic, we expect to be at the beginning to be sort of brittle. Like this linear after this elastic part, a short portion that can break. Now, if I increase the temperature, its module of elasticity is going to decrease slightly. So the slope of this line is going to change, right? So it becomes something like that. And then they breaks. And then there is a certain temperature where there is a relatively big drops in module of elasticity. And then we get to the point where the module of elasticity is becoming very small. So this is as we increase temperature. So this is then increase temperature. So this temperature somewhere in the middle where the module of elasticity has like big drops, we call it TG, or glass temperature, which again, if you recall, we talked about it and we said, let's say, if I draw module of elasticity as a schematic to give you an idea. Let's say this is E module of elasticity, which is the slope of basically these lines, right? If this is alpha, tangent alpha give me module of elasticity. So let's say at room temperature, I'm somewhere here for a certain material. Now let's say I'm increasing temperature. So x-axis is temperature. So this slope is gonna slowly decrease. This amount, module of elasticity is gonna be constant at the beginning, then a slowly decrease. And then there is a temperature when we can see a sudden drop and then again a big drop. So around that sudden drop, let's say around this point, we call it T glass or glass transient, which I can show it as well over here. Right, so this is the T glass, and don't confuse it by the melting point. So the melting point is so this is T glass, or we just show it by TG. And then the melting point is maybe somewhere around here, which it gets melted and module of elasticity gets to almost 0. T melt or Tm, all right? And you've seen it in that lecture for different materials, which show these T glass for different materials. Another property which is important for us is viscosity. So viscosity, all of you are familiar with it. In one of previous courses you've seen, is the resistance to shear, right? Or in other hand, let's say if I have my two hands, if I put a liquid between these two, right? How resistant they are if I want to slide my hands on top of each other. If, for example, between my hands, it's oil, it's easy to rub them against each other. If it's water, again, it's easy. If I put honey there, then you can imagine how difficult it is to slide them on top of each other. Now, if I put glue there, I'm not going to do that. Honey maybe, but glue no. And then I need a lot of force probably to slide them on top of each other, right? Shear to resistance. And just to refresh your memory, for each fluid, we have a constant, which call it viscosity. Let's say if I have two plates, I'm just showing it in 2D dimension. Let's say two plates. And let's say the bottom one, we fix the bottom one. And let's say between these two, there is a fluid, whatever. It can be honey or glue or anything, right? So that's the fluid, but it's not solid. Now, if I try to, let's say, move these, basically the top plate, and let's say with the speed u, all right, the maximum speed that I can move that on top. If I have my X and Y axis, let's see, I put my X axis here, and I put the Y axis there. So this is X, and this is Y, all right? So you've learned that basically, let's say at any point, maybe over here, the amount of force is going to change linearly. Or the shear force. Let's say at the top, the shear force is the largest. As we come down, the shear force becomes smaller, 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 and at the bottom, when it is zero, shear force is zero. And we had a relation for that, which was shearing force, tau, was a constant, which we usually show it by mu, changing velocity in y direction, right? And this mu is something we call it viscosity. To give you a viscosity, an idea for viscosity of different materials, you can see on this table, like honey is about 10, just approximation. And a liquid thermoplastic is about 100, like 10 times. So it gives you an idea that, like, if you imagine if you want to inject honey into, let's say, a small cavity, how much pressure you need. Now, 10 times higher than that. So that's the range of viscosity we are talking about, okay? Is there any question, guys, so far?
Is mu same as shear modulus?
No, that's totally different. Shear module of elasticity. So Ahmad asking, is mu same as G? No, G is for solid material, shear module of elasticity. If you recall, we have E, which is like module of elasticity, and then we have G, which has a relation with E and Poisson ratio. Sort of we can say they are related because the way that we define G, shearing module of elasticity, we say shear stress is equal to G, a constant multiplied by gamma. And this gamma is the angle that, let's say, if you have a solid, and this solid, you fix it to the ground, imagine a cube, and now you apply load at the top, try to sort of push it to the right, then it's going to deform, I'm just exaggerating, to something like that. And this angle, gamma, which we call it shearing angle. But somehow we can say they are analogy, but a little different, all right? So for a move, it's more like viscosity related to fluid, right? However, as you see, you can sort of say, well, here on this solid material, I'm also trying to deform it, and I'm trying to move every layer on top of another layer. So that's the shear stress between each layer. All right, now, does that answer your question?
Yep, thank you.
All right. So now let's get to the actual machine for injection molding. This is a typical, like this is a schematic for a typical injection molding machine. They can be, by the way, very small, like desktop size for small parts, to gigantic machines. But the concept is, for all of them are the same. Like most of them, let's start with this part, which is called hopper at the top here. Hopper is main, let's say, reservoir for putting the plastic pellets or granules into these hopper, right? That's where we start. We feed the plastic over there. And then the screw is the main or the most complicated part of an injection molding machine. Screw has 3 main functions. So let me write it there, functions of screw. So the first function, of course, it rotates and feeds the plastic into the mold. So it's going to be then feeding. All right. The second function is mixing. So it tries to mix different, like this plastic, some portion of it has been melted, some not. Because of this rotation motion and this like a screw type shape, it tries to mix things. Also, it has another important function, which is heating. Although we have, like most of machines, they have, as you can see over here, it has a heater bands around this screw, like outer layer, exterior of that, exterior of the barrel. And the screw is inside the barrel, and the basically there is a heater in most of machines. However, one important function of this screw is creating heating because of friction and pressure inside this plastic. So again, from one of those videos, hopefully you watch it, it explains the shape of this screw, which in the middle portion is not like straight, it's like it has been tapered, and it has an angle basically here to create more pressure, like on the image. If I can show you on the top, like as we go further to the left side, like this screw, the angle opens up to create a narrower, basically, let's say, pathway for the between barrel and a screw and create more friction. And then the rest is clear. We have the two halves of the molds, like the fixed part, you see here, the fixed part, and the moving part. The moving part attached to a mechanism, you can move left and right, opens and close when we want to inject things, and then open to eject basically the things out. And the rest are just a mechanism and so on. And at the bottom, you see the 3 steps of injection molding. The first is the step from the left is injecting. We inject plastic to the mold. The second portion in the middle is when we let the plastic to solidify, so the cooling. Sometimes it takes long, maybe 1 minute or so. Sometimes for smaller parts, it takes few seconds. To accelerate this process, sometimes people use like coolant or water around these two molds. It makes the process, like the mechanism and the machine, more expensive and higher maintenance, but it reduces the cooling time. And then the third is ejecting, which the two half of the molds will open up. So ejecting. And as you can see, the part is just falls down. And by the way, when we say a part, when we eject it, we are going to have the main part. But with the main part, there are like other portion of the plastic, which is like the gateway and the runners that attach to the main part. And they are going to also be with the part, which we need to trim it. So there is an extra process after ejecting each part. So extra. So this is extra plastics. But what are those extra plastics? If we look at the like a simple mold, let's say you want to make a cup, and this is just 1/2 of the cup. So let's say you want to make a cup, nice cup, maybe a soup cup. So the second half of the mold, I can add it here. So you can imagine this is the second half of the mold. So, all right, so this is the second half of the mold. And now you inject plastic there. So this is the main entrance that comes from that screw. So this is where you inject plastic. And let's say this cup that we want to make is like pinkish. So plastic comes in, goes to this part, which is called a sprue, and then goes to this section, which is called runner. And remember, this is all part of the mold design, and they are part of the mold. And then it becomes narrower, which is called gate. Gate is there to prevent like the part that hasn't been melted good, not let them to go in. And then plastic under pressure goes and fill all these gaps, right? So cavity, gate, runners, and a sprue. And sometimes we do multiple molds together, like this shape, as you can see on the left, which we have like the main parts, or like we are making, let's say, 4 discs like simultaneously. We have one sprue, and then we have the runners and branch runners, all right? And on this image, we show some spoons, like 10 spoons at the same time. So sprue comes and then goes to the main branch, and then the runner, and then the main branch to each spoon, all right? These are the main feature of injection molding tools. Now let's get to some calculation. When we design for injection molding, there are 4 parameters which we need to take into account. First one is how much force we need to hold these 2 half of molds together. The pressure to inject this plastic, the viscosity that we talk, right, is going to change that amount. And how much we need to cool the plastic. The shot size is relatively simple. The shot size is going to be like the volume of the parts plus the volume of the runner, the volume of the sprue, and the volume of the gate. We add all of them. This is what we call it, the shot size. In other words, in this image for these spoons, whatever you see in this image, all the volumes of it, it is called one shot size. it is important to calculate it correctly because under volume or over volume or overshot size result in defects. As you can imagine, if there is not enough plastic, it end up with some cavity. You end up with some cavity. If there is more plastic that we need, it's going to be something which later we'll talk about. It's going to be flash, where the plastic try to get out of the gaps or between the two half of molds and cause some issues. All right. But clamping force, pressure, and cooling time, these three parameters, force, pressure, and T cooling, are three main parameters which we need to calculate. And these can vary. If we have like a big parts like these containers or these big parts from maybe a boat or something, these two are totally different. Maybe they are both large. However, because the shape is different, the amount of force and pressure for each of them is going to be different. But how can we calculate that force? Let's do a quick calculation and see how we can calculate the force. For simplicity, let's say I want to make a very simple part like a cube. Okay, and let's say this is a rectangular, maybe box that I like to make by injection molding. And let's say this rectangular box or shape, and it's solid and filled, right? So let's say it has a length of L and the width of W and the thickness of H, all right? And if I show its 2D side, something like that, this is again H and this is L. All right, this is what I want to make. Let's put some coordinates there. So let's say at this corner, I put maybe X, Y, Z. So let's say call it X, Y, and Z, which is right hand, so that's good. So, and then from this view, this is going to be our X, and this is going to be the Y, all right? So here where the plastic comes to this mold, so this is the input plastic, flow into this cavity, all right? So let's assume the flow rate to be Q. So flow rate, let's see Q, which flow rate is volume divided by time, right? So then I can write down the time to fill up the mold is going to be, so it's going to be volume divided by Q, right? This is how long it takes for me to fill up all of these. So I can then write down time. It is volume for this simple example is WLH divided by Q. This is how long it takes for me to fill up this one, which is sort of obvious. Now let's talk about pressure, how pressure changes. So we know that pressure for a fluid can change, all right? So, and it depends if we have a turbulent or we have a steady state, laminar, constant flow. For simplicity, which is not really that far because with plastic, it's not high speed. The flow is not high speed. So let's assume that we have a constant and laminar and steady flow, then with this assumption, I can write down that the change in pressure in x direction is not linear, is not constant. It has something like this formula. Mu, which is the viscosity, change in velocity, second derivative of change in velocity in y direction, all right? So it gives us like a, more like a shape like this. So the pressure change, both in x and y direction. Now somebody tell me, what is the name of this equation? Come on, guys, you need to remember this one.
Is this part of the Navier-Stokes?
Great, Garrett. Yeah, Garrett was right. It is the Navier-Stokes equation, the famous equations for a fluid. So Navier-Stokes equation, all right? So with all those assumptions, if we try to solve this one, we will get delta P, the change in pressure from the beginning. Let's say at the beginning our pressure is P0. Here the pressure gets to P1. So this delta P, if we solve this partial differential equation, we'll get an ugly formula, which is like 12 mu Q L W H 3, H power 3. And this is an important equation, which gives us some hint how basically the pressure change inside the mold. All right. Now, if I want to calculate the force, which is more important for us, the force to hold the two halves of the mold together, right? So we know if we have pressure, the definition of pressure is force divided by area. So I can say then force is then the average of pressure between entrance and end, like P0 and P1. So it's going to be half of delta P multiplied by the area, which area for us here is W multiplied by L. Okay, so this is the amount of pressure we need to close to half of this mold together. Okay. So let's number these equations so later we can refer to them. So this is, or maybe from the top, the time that we require to fill like the cavity, let's call it equation 1. And then equation 2, the pressure inside the mold from the entrance to the end, let's say. And then 3 is the force we need to hold these two halves of a mold together. And it depends on the viscosity, the flow rate, and the size, as you can see. Let's quickly solve one example because I can see the time. In a couple of minutes, we will be done. So you can see how we can use this formula. I'll let you quickly read this one. I'll do the same so I can then figure out how to solve it. So we have a plastic, of course, and we know the length, and we know the width, and we know the thickness. We know the change in pressure or the drop in pressure, delta P. We want to find out the time it takes to fill the mold, all right? And also we know mu. So this is the information that we have. So let's see what we have from equation 1. I know the time. So the time was WLH divided by Q. From equation 2, this is all the tools that we have, right? It was equation 2 or 3? 2. So delta P, the pressure is 12 mu QL divided by WH3, right? Here, let's see. We have everything except Q. If I get rid of Q, then I can simplify these equations. So from 1 and 2, I can get T, so 1H. I can get rid of 1H. So T then is going to be 12 mu. Please check my calculation later. And it's going to be L over H squared, right? So maybe another nice formula, which independent of flow rate, we can find out the time that we need to basically fill these things. So from here, you can find T. Second, I'll let you guys to do that. So I'll let you guys to think about it for a moment and see if you have any question. So all I did just equation 1 and 2, I just get rid of Q because in this question, I don't have any Q. And we got to another formula, right? And this is the time that we need to basically fill the mold, right? It's different than the time that the mold needs to solidify. We haven't talked about it yet. And quickly, let's look at this example as well. Let you guys to read. See, I just want to say how simple it is. So you have injection mold, which the pressure drop is 15 megapascal. And the length, you have the length and the width. You need to calculate the force. Well, that's super easy, right? Because we have a nice formula. Force is half of delta P multiplied by the area W multiplied by L. So these values, 4 and 25, this is easy. What else we need? We have 15, we have W, L, and divided by halves. It's going to give us 75,000 Newton. Again, please check my calculation, but that's megapascal. So you can imagine for this small size, a quarter of a meter and about 4 centimeter. So you need a lot of force for this part. All right. So that's it for today. The next parameter that next lecture will talk is about the cooling time. How long does it take for 2 molds? How long does it take for the plastic to solidify? Which is again an important parameter, because if we open up the 2 half of the molds too fast, then you know what's going to happen. Too late, we're just wasting time. All right, that's it. And also next lecture, I'll talk about the different geometrical features when we design for injection molding. If you guys received my 4 or 5 weeks ago before semester announcement, I suggest that you order this cube. I'm not sure if you did. Maybe this year because of COVID, you receive it late, but hopefully you receive it. But last year, most of the students, they got it. Some of them, they got it late. Anyway, so that's, we'll talk about it in next lecture. If you haven't, it's free. It's another piece of plastic. If you're concerned about environment, don't worry about it. If you like to have this cube, it can, basically you can make the cube and all these parts. That's why we call it cube. It has a nice feature, which I'll talk about it later. So you can get this nice cube. All right. That's it for today, guys.